Alrighty, y'all. Are you ready to learn? Today we're taking a look at our recitation for April 29th. And for this one, we're going to be looking at transmissions and gears and various other things. Right? So we have our two limitations on motors. We are limited in the amount of torque we can apply and our angular velocity at which it can be applied. Right? So we use the example of a human riding a bike. We can only push so hard on the pedals and we can only pedal so fast. So the first thing we're going to do is figure out the maximum power that our motor can deliver to the machine. Okay, so we're given a maximum torque and a maximum omega, and we're also reminded that our favorite equation, not our favorite equation, our lovely equation, right, that our power is equal to force dotted with our velocity. And just like with most things, right, our rotational mass is just the same equation, but with the analogous bits and pieces, right? So power is going to be, right, our version of force in the angular zone is torque, and our version of velocity in the angular zone is our angular velocity, our omega, right? Same way when we do our sum of our forces, we can do our sum of our torques, right? They're related. There's the analogy there. And the same way we can say our meters per second, this is our radians per second, right? How fast we're going around the circle. All right, and we are given this handy dandy chart in the back. Oh no, it's sideways. All right, I guess I'm not going to be using that chart, but we can keep thinking about it as we go. So now that we have our equation for power, we need to figure out our maximum power. All right, so if we're getting our maximum power, we're going to be using our maximum torque and our maximum omega. So if I plunk that into our equation, our maximum torque is 100 Newton meters, and our maximum omega is 50 radians per second, giving us a maximum power of 5,000 watts. Right? And watts is power is our rate of doing work. Watts is our energy per time. It's joules per second. So that is our maximum work. Our maximum power, sorry. Right. Well, now we have to figure out how it can run at different speeds. So now we're wanting to run our machine at a low speed, 25 radians per second. So we're still going to be using our maximum torque, but we have to figure out how much power we can be delivering in this case. Okay. So given that our power is force times, not thinking right. Power is our torque and our omega, right? The maximum power we could deliver in this case would be our maximum torque, but 25 radians per second. So if we have our power, it's going to be 100, our max torque, but this time we're only multiplying by 25, which will give us 2,500 watts. So we can only deliver, right? If our machine is hooked directly to our motor, we can only deliver half as much power because we're only going at half the angular velocity because our motor is only running at half that angular velocity. Now, to fix this problem, we're going to start adding some gears. All right? So we can't go any faster than 50 radians per second. So if I go down to my chart, it's a little sideways, but we can still take a look. If we're hooking we have no gears, so our motor is connected directly. If we want our machine to be running at 100 radians per second, but it's hooked directly to the motor, our maximum omega is only 50, so we can't run our machine that fast. This is impossible the way we have it currently set up. Okay? So moving back up and flipping back to facing the right direction, I guess. We have to start figuring out how we can fix this problem with gears. Because we still want to be able to exert our maximum power, but we want to be able to run at any speed. Right? So let's figure this out. So we have constant angular velocity. Right? Motor applies a clockwise torque to the red gear. Right? So here's our motor applying a torque. Ooh, that is a wonderful arrow that I just drew. That's a little better. Here's our torque from the motor. Clockwise torque the red gear, but the blue gear applies an equal and opposite counterclockwise torque, right? So the teeth, right, they're going to be pushing on each other. So if our torque of the motor is spinning us this way, right, we have some kind of counterclockwise torque here between the two gears. And if I look at this, right, same thing. We see we're told that we're reminded of Newton's third law, right? Our forces are going to be equal and opposite. So if there's some force between A and B here, here's our force between B and A, they're going to be equal and opposite. So we have these two forces, but we're still at a constant angular velocity, which is the fun part. This is giving us a counterclockwise, so we're going to be given, okay, so this is making us clockwise, this is counter, this is counter, this is, I had to double check that for a second, right? Because this gear, the whole point of this gear is that it's giving some output torque on the machine, and some kind of torque is getting output, right? So we have our input torque here from the motor, forces are equal and opposite, and we have our output torque here. So now we get to figure out our relationship between things. So if I start with some of my torques on this, right, so our red gear, we have the input torque going counterclockwise, or going clockwise, sorry. And then we have our torque as done by the blue gear, right? So I'm just going to call this F because it's the only force we have. Since it's doing a clockwise torque, it's going to have our counterclockwise torque, right? It's acting counterclockwise, so it's going to have a positive torque. All right, we're told it's a constant angular velocity, so our alpha is going to be 0. And I use this R in because that's going to be the radius of our input gear. All right, so there's some of our torques on that one. Now if we do our sum of our torques on the blue gear, now we have, all right, we have T out also acting negative, still going clockwise, but we have our F times R out, because this force, and I'm using the same letter for them because it's equal and opposite forces, F and F. This time the torque is our big radius, our R out. I'm leaving everything in terms of these R's so that I can get a clean relationship. And then eventually I can plug in any radius so I can get the relationship between the two torques in that situation. It is tempting to say, oh, the torque that I do here has to be the same as the torque. But that's not Newton's law, Newton's third law. Newton's third law said that the forces are equal and opposite. I can't say that FR in is equal to FR out, because if these forces are supposed to be the same, but these radii are supposed to be different, there's no way that they could be equal. So we can't just set it up like that. We have to solve this on out, plug on into the other one. So I'm going to solve this for F. So if I bonk this to the other side, T in, and I'm going to divide by R. Solve for that force. Now they're equal, so I can take this and plug it on in over here. Right, and if I bonk this to the other side as well, I'm going to get that. T in over R in times R out equals T out. Okay. So, right, if I simplify this, right, it mentions something up here, get our gear ratio. So if I know my input torque, right, I have the R out over my R in equal to my torque out. Right, so I have my input torque, I multiply by my gear ratio, it's going to give me my output torque. Cool. And now we're going to relate the velocities of the gear teeth, right? The velocities are going to be the same as they turn, because Because if I zoom in super duper close, right, the teeth of the gears are just kind of, you zoom in close enough, they're moving in a straight line, and they have to be moving at the same velocity in that straight line. Otherwise, one teeth of the gear is going to be slipping through the other, and they're solid objects. They can't pass through each other like that. But now we have to figure out, we're going to use that information to get a relationship between our omegas. The same way that we did before, we could say that the forces were going to be equal, but we couldn't say the torques were going to be equal. Now we can say the velocities are going to be equal, but we can't say that our angular velocities are going to be equal. So let's figure this one out. We know that our velocity, let's think about our red gear first, I guess. Right, it's r times omega. So in this case, it's going to be our r in times our omega in, or our omega of the motor. Right, it just uses different language for it, but that's fine. And we also know that for our blue gear, the velocity of teeth is going to be our r out times omega out. Well, we said that the velocities are equal. Here's our relationship. You can just set these two equal. R in omega in equals r out omega out. Technically, right, if I look at this, right, we know that this gear is going to be spinning as it's being motored around here. This one's going to be spinning clockwise. This one's going to be spinning, goes like this. This one's going to be spinning counterclockwise. So technically, if we want it to be correct, we smack a negative sign in there. But really, this is for like thinking about magnitudes, and we can say the magnitudes of is however fast it will be going, ignoring the fact that they're going to be going in opposite directions, right? So if I finagle this around a little bit, right, to make it look kind of like what we have up here, we're going to get another gear ratio. Oh, it's supposed to be our big R. Right, so I have that my omega in times my R in. If I divide both sides by that R out, that looks like a K. That is an R. That's going to equal our omega out. So we have another gear ratio, but this one's upside down of our last one. But either way, here are our two relationships. And again, we don't care which way we're spinning the machine for right now. All that means is that we're going to end up flipping their directions, but we're just thinking about how much power, how fast it can go. We're looking at speed more so than the velocity, and how much torque it can apply, again, not caring positive or negative right now. All right, so there's our relationships for down here at our chart. Our relationships between them using those gear ratios. So now, if I go back up to more questions, we have that our motor is running at a maximum angular velocity and torque. All right, we were given that before. Our maximum angular velocity, 50 radians per second. Our torque is 100 newton meters. So we have an output gear and our given input gear, right? 10 centimeters. All right, so R in equals 10 centimeters, and I'm just going to get that directly into meters because, right, base units, we want to keep everything consistent. And our R out is 20 centimeters, or 0.2 meters. So now let's figure out our angular velocity of the machine, and the torque, and the power that's supplied to the machine. Well, it says to enter it in the table, but I'm not going to be writing sideways. We're just going to be figuring it out. So let's figure out our everything, right? So we have that our omega in is our 50 radians per second, right? Because that was given above. And our torque in is 100 newton meters, right? Because again, we're at our maximum, so we know these. And we have our radius in and we have our radius out. So we get to use the relationships that we just wrote down here. Well, I wrote them up here, but we get to use these relationships because we have input and the two radii, so we can get an output. We have the input and the two radii, we can get our output. So if I steal that equation here, I'm going to go like this and this. So output radius over input. 0.2 over 0.1, that's going to equal 2. So T in times 2 equals T out. And our T in is 100, meaning that our T out is going to be 200 newton meters. And our omega in times 0.1 over 0.2 is 1/2. Equals our omega out, which means that since we're going 50 radians per second, now we get our 25 radians per second. Right? Well, we finally figured out how we can get another way to get our 25 radians per second. Now let's figure this out, right? We're at our maximum omega, maximum torque. Let's figure out the power that is supplied to the machine. All right, so we said before, power is just torque times omega. So let's take our torque times our omega. So it's going to be 200 times 25. All right, that's going to come out to 5,000 watts. All right, because our power before, we had our 100 times 25 was half of it. Right, but here's our maximum power, our 5,000 watts. Now we figured out how we can run at 25 radians per second. We can run our machine 25 radians per second, but still supply it with the full 5,000 watts of power. Because, right, if we double our torque and half our omega, we multiply them out together, it's going to be the same thing. Right? So how does it compare to the maximum power that the motor can deliver without the transmission? It's the same, right? Energy is conserved. Whatever energy we're putting into the machine, it has to be the energy that's coming out of the machine. Like however much energy that the motor is putting into the transmission, right? Our angular velocity isn't changing, so that's going to be the same energy that's going to be being used by the machine. Right? So now we want to be able to run the machine at an angular velocity of 100. Right? So we're getting that our omega out equals 100 radians per second. Right? We want to run the machine that fast. That's going to be our output omega. Now, it would be impossible without a transmission, like we said before. Right? When we wanted to run it at 100 before, we said we couldn't do it. Well, now we have gears, because our maximum omega here, now we have gears and solves this problem. So what radius should the output gear have so the machine can spin that fast? So let's figure this out. All right? If we say that our omega in is going to be 50 radians per second, right? We want to be running at that max power. We want to be running at that maximum omega. So we know that omega in times, right, R in over R out, and that has to equal our omega out. Right, so we're trying to find the radius of the output gear. So we already know our radius of the input gear. That was staying stationary from before. Now we get to see, right, if I plug this in, 50, 0.1 over R out has to equal 100. Okay. So now it's just algebra. I'm going to bonk this over to this side, divide on through. This is going to end up being 50 over 100 times 0.1. So this is going to be 5 over 100 equals R out. That is a 5, not an S. Right? And 5/100ths, so that's going to be 0.05 equals R out. And again, since I was keeping all my everything in meters, this is 0.05 meters or 5 centimeters. Okay. Okay, so if we wanted our omega to be faster, we're going to decrease that outer radius, the output radius, right? Which makes sense, right? Because when we wanted to decrease, when we were decreasing R, when we had a larger R than we had in, when we had a larger out than we had in, that gave us a smaller output omega. But now, if we want a larger output omega than we have input, we need our output radius to be smaller than our input. It's kind of tricky with all the ins and outs, and I'm not pronouncing hour properly, or like hour versus R versus hour versus whatever's going on. Just bear with me on this one, but we're just remembering how all this works, I guess. We're learning. That's all we're doing. Right? So now we need to use the same motor to generate a very, very large torque. So we're lifting something super heavy. So we need the output torque to be 1,000 Newton meters. Which again, if we were going back to just the motor, that's not possible because the max torque we can do with just the motor is 100 Newton meters. So what two radii would we use for the gears? So we know our relationship between our torques. If I borrow this from up here, you know that torque in, right? We want that to be our max. R out over R in equals, we want our output to be 1,000. So here she is. If I divide both sides by 100 real quick, we're going to get that our output radius over the input radius has to be, remembering how to divide, that's going to be 10, right? So we know that whatever the radii are, which we're not given one of them, so we can't just, there's not one definitive answer. We can have a bunch of different radii. The two radii, what are two radii you can use? Well, it could be any radii that fit this ratio, meaning that the output radius is going to be 10 times the input radius. Right? So whatever it is, we want the output radius to be a whole lot bigger than that input radius. That's going to be increasing our torque. So an example of something that would work, R in is 1 meter, R out, that's supposed to be big R, is 10 meters. Okay. 1 meter times 10, 10 meters. Doesn't really matter, could be anything. Right? Using the same radius R in from above, right? If I wanted to do that, it was 10 centimeters. So if I really wanted, we could say R in is that same 0.1, which means that R out would be 1 meter. Right? Doesn't really matter. All of these work because it just needs to hold this ratio. That's all we need. It could be anything. You could do pi and 10 pi, though I wouldn't recommend it because that'd be very tedious. Right? So now let's start thinking about applications of this, right? We had some arbitrary motor doing some arbitrary thing to a random machine that we didn't know. But now let's think about a bike. Right? For those of us that have ridden a bike, wonderful. It uses gears and chains. It's so much fun. But we all generally know what a bike is supposed to do. So now we're applying it to things that you may have seen before. And again, the legs are limited in torque and angular velocity. I can't push infinitely hard, and I can't pedal infinitely fast. So we want to apply a maximum power to our output gear. Right? So that means we're going to be at a maximum torque and a maximum angular velocity. So we get to figure out how that's going on. So we climb a steep hill at low speed, go as fast as possible on low ground. So what combination of gears would a rider want if we're climbing up a steep hill at a low speed? Well, we want our omega out to be pretty small. So I have my relationship over here from our omegas. Oh, come on, there you go. if my omega output is really, really small, and saying we're still at our maximum omega input, right? This isn't changing. This is still at the maximum, so we don't lose any power. We get to figure out how we can decrease it without changing our omega. So if we're trying to decrease this, there are multiple ways we can do that. We can either increase our denominator or decrease our numerator, meaning that Rn, you want to decrease, so that's in the numerator, and R out, you want to increase, because increasing the denominator makes this whole thing smaller, makes this whole thing smaller. So you want a small input gear and a big output gear for a hill. Right? But if we're going very fast on flat ground, right, it's the opposite. So if I steal the equation again, this is still being held constant, but now we want our output omega to be a lot faster. So the way we accomplish this, we can either increase our numerator or decrease the denominator, or both, right? Increasing this, decreasing this, increases all of this, increases all of this. Holds this ratio, holds this relationship true. And now, what capabilities do a transmission study what capabilities does this provide? Do transmissions provide? Well, how can they extend the capability? Well, now we said before, we could have a much bigger torque than originally thought, or a much different omega than we thought. And this is things for like cars and whatnot. All right. We can go fast, we can go slow, we can figure out what's going on, all those kinds of things. It means so we don't have to just run a motor at our one given omega in order to get this maximum power. We can do different kinds of things, but still get that max power. Because we want to be putting as much, like we used an engine that can put out however much power. We want to be using all that power when otherwise we should have just put in a smaller engine. And the same thing. Now we're looking at, can a transmission increase the amount of power that we can produce? Well, we already kind of looked at this, but no, we can't increase the amount of power. We can increase torque, or we can increase angular velocity, but we can't increase power, right? Because as I increase one, the other one's going to decrease to keep it the same. Same thing, right? We have that conservation of energy. We can't create energy out of nothing, right? The energy has to be coming from somewhere. In this case, it's the power being supplied by the motor that's then going to be used by the machine. So however much is being added, that has to be the same amount that's being used. We can't be using more than we're adding, otherwise that energy is coming from nowhere. Right? This is another way that we can look at our relationship between the omegas down here. It'll work out to the same thing. But if I say that the power produced by one is the same as the power used by the other, right? So power in equals torque in omega in, and power out equals torque out omega out, right? If we know that we have our relationship between the torques, I'm just going to steal it from here. We know we had it from up at the top too. If we know we have this relationship here, this is solved for T out. I'm going to plug this in here, and I can set power in and power out equal. So I get T in omega in equals T out omega out. And then I take this and plug it in over here. It's going to give me that T in omega in equals T in, that's big R, little r, omega out. I divide T in from both sides, and that gives me that same relationship that we just had, R out over R in, omega out. The only difference is, right, up here, I had it solved so that it was set equal to omega out. This time it's set equal to omega in, but if I divided both sides, it would give us the exact same gear ratio, right? Opposite to this one. So looking over here, this is kind of what we talked about. All right, we said with all this motor stuff in the middle when it's connected directly to the machine, right, with the no gears. This one's not possible, but now, since we have gears, we can do so much more, and so much more is possible. So this is very important, very, very important for engineering applications, because it can allow you to accomplish a bunch of different things without having to switch out your motors. All right, well, I hope you found this video at least a little bit helpful. Let me know if you have any more questions about this recitation or any other problems that you want me to try to explain, and I'll do my best to try to explain it, because I guess Sydney explains stuff.